What is hot in antennas and propagation? Today I'll present to you the highlight of our paper, Scanning Angle Extension of a Millimeter Wave Antenna Array Using Electromagnetic Bandgap Ground. This is a collaborative work of Xidian and Xianjiao University. I'm Professor Zhao from Xidian University, and the corresponding author is Professor Chen from Xianjiao University. This presentation will be composed of 5 parts. First, let's talk about the motivation of this work. As we all know, 5G is gradually migrating to millimeter wave bands to deliver data with higher throughput. At the same time, due to the propagation characteristic in millimeter wave bands, path loss has to be dealt with. Therefore, phased array is widely used for millimeter wave communication systems. We can see thousands of antenna elements at the base station side and tens of antennas at the mobile terminal side, creating high-gain, precise, yet narrow beams. Therefore, wide coverage capability is needed not only for communication but also for sensing applications. To create a uniform linear array with wide scanning angle, the following 3 key factors must be satisfied. Firstly, the element spacing has to be reduced to around 0.5 lambda to increase the effect of array factor at the large scanning angle. Secondly, according to array pattern multiplication, the element pattern has to be broad. Finally, the mutual coupling between the closely spaced elements have to be dealt with simultaneously. To satisfy the above 3 requirements seems to be very challenging, thanks to the bandgap and in-phase reflection characteristic of the EBG structure. If we place well-matched antenna elements above the EBG ground and form an array, the 3 requirements can be satisfied at the same time in the same band. In our design, E-shaped patches are selected for better impedance matching. Mushroom type of EBG structures have perfect bandgap property from 24 to 28 GHz. At the same time, the in-phase reflection condition is also valid in the same frequency band, as can be seen from the figure here. To clearly review the coupling mechanism between 2 E-shaped elements, we also developed a circuit model, which matches the physical model in both the magnitude and phase responses. It is clear that the isolation between every 2 elements is more than 17 dB. The array is fabricated using multi-layer PCB technology. The layer stack is shown here. The SMPM connectors are using as the feeding ports. The scattering parameters are measured with a millimeter wave VNA, while the scanning performance of the array is evaluated in the spherical near-field chamber with a programmable beamformer. The measured scattering parameters show that the array with the EBG ground outperform the array with the PEC ground in both the bandwidth and inter-element couplings. More importantly, the scanning angle can improve from 55 degrees to more than 77 degrees with less than 3 dB scanning loss, which is confirmed by the coverage efficiency comparison. That's all for the highlight of this paper. Thank you for watching.
Dear all, thank you for the chance to introduce our recent work, Compact Millimeter Wave Array with Wide-Angle Scanning for Mobile Phones. For the background of the arrays for mobile phones, the antenna element is mostly based on 0.5 wavelength resonance, and takes 0.5 wavelength to structure the array. The length of the array is about 2 wavelength, which is a bit large. A high side lobe level will appear at wide-angle scanning, which will result in a limited beam scanning range. Here is our idea: the array with close spacing can achieve a wide-angle scanning and small size array. As can be seen, the array factors of the array with 0.3 and 0.5 wavelength spacing are similar at small steer range. But at the 60 degree, the array with 0.5 wavelength spacing shows a high side lobe, while the array with 0.3 wavelength spacing keep a low side lobe level. So, this idea is effective, but there are 2 difficulties: how to achieve small element and how to reduce array mutual coupling. Here is our small element design process. ANT1 is a conventional probe-fed 0.5 wavelength patch antenna. Adding shorted pins at the center of ANT1 to the ground, the patch size can be reduced to half, but as the red lines show, ANT2 suffers from a high XPL in H-plane. To reduce the XPL, the coupled shorted structure is designed in ANT3. As the green lines show, there's a reduced H-plane XPL. Based on ANT3, the coupled feeding structure is used in the proposed element, there is a further size reduction and a better H-plane XPL. Then, a 4-element array with 0.3 wavelength element spacing is designed. 3 neutralization lines are used to reduce the mutual coupling from -8.9 dB to -15 dB, and the array shows a -10 dB impedance bandwidth of 25.5 to 27.5 GHz. To check the performance of the array, the scanning beams are shown here. As can be seen, within plus or minus 60-degree beam scanning range, the gain fluctuation is only plus or minus 0.75 dB. Also, the proposed array has a low SLL and a moderate XPL. Compared to the array with 0.5 wavelength spacing, there's a significantly lower SLL. So, the proposed compact array with close element spacing can achieve a good wide-angle scanning. In conclusion, a compact array with 0.3 wavelength spacing is designed. Which size is the smallest? 3 NLs are used to reduce coupling and a wide beam scanning range is achieved. With compact array, mmWave technology is easier to access in mobile phones. And faster wireless connectivity could be available for the public. Thank you for your watching.
Hello everyone. It is my great honor to present our research on the wide-angle beam scanning millimeter wave antenna array using phase-controlled beam-steerable elements. Recently, millimeter waves have shown great promise in many application areas due to their high accuracy and high transmission rate. The proposed millimeter wave antenna element has a dielectric substrate layer and 2 radiators, which is square microstrip patch and a square microstrip loop. The square patch is located in the center, and surrounded by the square loop. When port 1 for the patch element is excited alone, the predominant surface current flows along the x-axis, and exhibits a half-wavelength distribution. It indicates that the patch is operating in the fundamental mode of TM10. When port 2 for the loop element is excited alone, the current flowing along each side of the loop exhibits a full wavelength distribution. It means that the loop operates in TM22 mode. When ports 1 and 2 are excited separately, the distribution of electric fields of the patch and loop accord with the sketch, resembling the characteristics of the TM10 and TM22 modes, respectively. By synthesizing the radiation patterns of the patch and loop elements, the direction of the main beam can be reconfigured by adjusting the phase difference between the 2 ports. This is the simulated 3D radiation pattern of the proposed antenna element with 3 beam switching states. When the port 1 is excited, the antenna element has a broadside radiation pattern, which is state 1. And the beam direction is switched from -45 degrees to 45 degrees with phase difference tuned from -90 degrees state 2, to 90 degrees, state 3. 8 proposed phase-controlled beam-steerable antenna elements are arranged linearly in one row. The spacing between adjacent elements is 0.75 lambda. The overall size of the phased array is 6 lambda times 0.75 lambda times 0.07 lambda. This is the prototype of the proposed array. We obtained the beam scanning radiation pattern using the active element pattern method. The active S parameters of the proposed millimeter wave phased array still maintain a working bandwidth from 26 to 30 GHz, and the proposed array exhibits a peak gain of 13.2 to 13.6 dB in the normal direction. Within the operating frequency band of 26 to 30 GHz, the proposed phased array achieves a 3 dB scanning range of plus or minus 76 degrees with a grating lobe level of less than -5 dB. Compared to related works, the proposed millimeter wave phased array has a wide beam scanning range with a compact size and simple structure. Thank you for your listening.